Hey, cool.
Nice.
Thanks. Hello, everyone, and we are for our fourth season episode of our lectures on the Hacker Cup. We are today with Kilian Lieret and Mark Sarufan. Kilian is from Software Engineer Agent, and he will be talking us about this amazing tool that we actually use also internally, and how can you leverage that to try to solve some of the hardest problems in programming from the Hackers Cup. Hello, Kilian.
Thanks a lot for the nice introduction. Pleasure to be here. Very exciting to be live. I guess should I just start with my slides already? Nice. So, showing my whole screen because we'll actually do some live demos later. That hopefully will work. All right, so I'll be talking about SWE Agent, where SWE stands for software engineering, if that's not obvious. So lots of people involved, very exciting stuff. Most of the credit goes to John and Carlos, who lifted this whole thing off the ground, and I joined around half a year ago. I have a background more in AI for physics, and it's been only recently that I switched to NLP and this project. And I'm a little bit more on the engineering side, and I will also talk you through really how to use it, how to adapt this tool. But if you have like very broad AI questions, I might have to pass them on to the rest of the team. So just to give a little bit of an overview of the ground that we'll cover in this talk, I'll start by giving a little bit of background about SWE Bench, which is a software engineering benchmark for language models. And this was the primary motivation to build SWE Agent, as you might guess from the naming. Nonetheless, even though that's like a slightly different task than more like the coding challenges that you're probably most interested in if you listen to this live stream, it's a very versatile tool, and it can be adapted to a lot of different things. That's a very good baseline or starting point to build your own system. So that's part one. Then part two is basically covering what we in the SWEAgent paper, and it's mostly about how can we optimize the tool that we give to language models to become useful agents. So the big buzzword there is the agent-computer interface. How can we optimize that? And finally, chapter 3 and 4 will be the stuff that makes me quite nervous, because that means like giving you a little bit of a quick start, running some stuff live so that you really get a feeling for how a SWEAgent would look like in practice. And the last bit, tweaking, tuning, hacking, is really about how can you configure SWEAgent, how can you tune it for what you're doing, and also a little bit of a quick start to how actually touch some of the implementation details, because it's not too complicated, so you can actually really easily modify the behavior at any level. All right, so let me start with the first bit of background. And this is first about taking a look at other benchmarks rather than SWE Bench, which oftentimes have a form like the thing you see here. So you have a little bit of a function signature, solution takes a list, and you have a doc string which explains what this function should do. And it's a very common form of benchmarks that we then ask the language model to fill in the blank that we highlighted in yellow here. And it's quite nice, but there's a couple of limitations which make this actually a relatively easy benchmark. For example, the whole context is just, here it's just 10 lines. It's really short. Then it's a very isolated task, also because we usually, in those challenges, we emphasize primitive Python. So there's no library, and there's just not a whole lot of context or other knowledge to incorporate here. And also for the usefulness, if we think about, well, all benchmarks should really demonstrate or like go towards an application of language models, and this mostly applies to writing code. It's mostly about, if you want to improve GitHub Copilot or do any kind of completion systems that help you writing code, this is kind of a realistic benchmark. But for any of you who are doing software engineering, usually, the times where you like write long bits of code are, like it's not that much. Like most of the time is spent on having like an already large application and just editing or like debugging very small parts of it. And here this benchmark just really doesn't apply. So instead of this, what we look at is kind of the normal workflow of a open source software development project. So you might have a big repository, maybe with hundreds of thousands of lines of code. And people are already using it. Maybe you're already using it. And at some point, you'll find a bug, and you report it by creating an issue on GitHub, for example. And hopefully, someone sees that bug, or even you yourself start investigating. And at some point, there will be a pull request with a patch to address this issue. Now, of course, it could also happen that you just be told that, oh, it worked on my machine and it's a user error. But so we'll have to do quite a lot of filtering to really get these pairs of issues to pull requests. This is really what we want to hone in. Like SWE Bench is a benchmark that consists of real world issue to solution pairs of this stuff. So for that, we pick a repository. We go through all of the pull requests, make sure that they're actually associated with an issue. And in this way, we selected 12 repositories with a lot of stars and a lot of activity in them to make sure that we kind of get high quality content. Then we do a little bit of what we call attribute-based filtering, mostly checking that there's tests and that there's new tests that are introduced in the pull request. That's very important for us to then later verify the solutions by the language model. And we also have some subsets of SWE Bench, for example, called SWE Bench Lite, that have a little bit more heavy attribute-based filtering, just to make sure that we kind of pick out like the most realistic and the most high quality issues here. And finally, we do what we call execution-based filtering. So we make sure that we can install the environment of the repository at the time where the bug or the issue was reported. We can install all the dependencies, and we can run the test before the pull request was merged, and we also can run the tests after the pull request was merged. And overall, the challenge here of this benchmark is that these repositories are really large. So we're talking about an average of 400 to 500,000 lines that you obviously just can't completely pass to a language model. In contrast, and this kind of goes back to that software engineering is mostly about modifying small parts of code rather than like writing huge chunks of new code. On average, those solutions are relatively small, only 12 lines changed on average. And in fact, there's quite a significant portion, maybe 10 to 20%, that can even be resolved by changing a single line. So it's a really interesting task for language models to go at. To look at one of these in details, this is an example from SymPy. There's a library for symbolic manipulation and symbolic mathematical operations in Python. See here on the left side, this is basically about how a certain expression is displayed when you just use this in a Jupyter notebook or in interactive Python. So this is the issue on the left. And what we see on the right is what's being introduced by the pull request. And that has two parts. There's a test patch, meaning that there's a new test that is being introduced to make sure that there's never going to be a regression of this issue. So this both then verifies the solution that's currently being submitted and makes sure we don't kind of fall in the same pitfall again. And then there's the human-generated solution, which we call the gold patch. So this is the pairing that makes up SWE Bench. And now if we evaluate SWE Bench with any kind of language model or any kind of agent or system, the input to the system will be the issue text and the entire code base. Obviously, you're not allowed to use anything of the gold patch, not the new tests, but just really the code base at the point and the issue text. We also exclude all the issue comments because they might already kind of leak the solution. So this makes it kind of a realistic setting, just as if you found the issue on GitHub and now want to solve it yourself. Don't have any more information in this. Now, the language model or language model agent then generates a pull request, which we represent by a patch or the git diff of whatever edits are being made. And then we say this is submitted for evaluation. And then we basically evaluate all of the unit tests after this pull request was merged. And obviously want to make sure that all of them pass. You can see that there's also a pre-PR column. Those are the pull requests. Those are the tests that include kind of the test patch, but not the human solution. So those are the new tests that really check that the issue has been fixed, and we want them to go from fail before the solution was applied to pass. So this is another filter criterion from SWE Bench to make sure we only have task instances in there that are tested to some degree. Just to give some baselines, the simplest thing that you can do is, you take all of the issue and all of the code, you add a little bit more kind of prompts to the language model, and you basically try a one-shot generation. You just ask the language model to come up with a patch. If you do that, you'll solve, let's say, around 5% of the simpler subset, SWE Bench Lite. So that's not really great. It's actually, so the 5% is already slightly inflated. So you get 4% if you do some kind of simplistic context retrieval, like if you just search for relevant bits of the files with BM25 and only append those to the big prompt to the language model. But even if you use the context from the gold solution, you only get to 5% if you kind of do this naive way. So this is kind of good because it also means this is like a really hard task and motivates, of course, to try something slightly more complicated than just directly one-shot querying a language model. Now a fun fact that's more recently surfaced is that you actually can get surprisingly good pass@k rates for this. So if you just keep on trying this, you don't only do this one time, but like 50 times, so you get 50 patches. It's not so unlikely that one of them will actually solve the issue just because you tried many times. And even though you didn't execute any code or check anything, like one of the solutions might just work. Now, of course, pass@k is different than pass@1, and it's not realistic. But there was the paper called Agentless, which combined this generation of 50 attempts with a ranking system. So they kind of try to always use another a language model to rank the different solutions and submit the best one. And that worked really, really well. So it doesn't always have to be an agent. But agents are also really interesting because they allow us to basically mimic the development workflow that a human has, and obviously give the language model much more input from, for example, code execution, and give much more information to verify what's going on. So this is the motivation for SWEAgent. Basically, we basically set out to mimic the human-style iterative development workflow, rather than just like compiling all the context, giving it into a language model, asking it to generate a patch, and then stop there. So let's look at this human development workflow for a moment. It probably looks something like this. You have a bug. You start finding or reading all the relevant code, or at least enough to really reproduce the bug. Then maybe you go back to reading some more code, you make some edits, you run the reproduction script again, or add some tests, make sure that it's actually resolved, and then you're done. Except that for most people, it actually looks more like this. Like there's a lot more things that are going wrong, and oftentimes you just change stuff, see what happens, get really frustrated. And it's like a lot of, it's not only highly iterative, but like you jump back and forth between those steps a lot. And actually SWEAgent does that as well. And even sometimes, just like humans, it loses patience and tries the same thing 10 times over, and that's obviously not very good. So this is like already like a really interesting system, just because of kind of like the likeness to what humans do. All right, so let's look a little bit more closely at the findings that we had from implementing this. And first, let's compare it to something very naive, which is just, we could in principle just give GPT-4 access to the terminal. So we have the GitHub issue, we have the code repository. Let's just give the language model the issue text and tell it to just run commands until it thinks it fixed that. So, the model would start, like typing ls, and then would discover some files, maybe would do something slightly clever and like search for a file by name or use grep to really search for strings, and so on. And then it might edit in some ways. Unfortunately, that's not really easy. And I'd say that, like using only bash commands, like pure bash commands, is already hard for humans. And as humans, we always, like use like slightly more sophisticated tools. It might be VS Code, or it might, for example, be Vim. So Vim is not, technically a bash command, and it's like more of an interactive program already. So both of these are actually not, are not easy to hand over to a language model. Like with Vim, you have the issue that, it's a lot of very finely granular movement commands or like a sequence of key presses that are required. So that's, not, you can, of course, make GPT-4 use Vim, but, it's going to struggle. And similarly, connecting it to VS Code has its own, box of problems. So, the key thesis of the SWEAgent paper is this notion of an agent-computer interface that will probably look different than the interfaces that humans look, but is also very much optimized so that the language model has the information it needs at the time where it needs it, and also can really understand it and follow up on them. So to put it in a small cartoon, we have the language model here on the left, and then we have the file system and the ability to execute stuff on the right. And the agent-computer interface is what mediates here. So that means the agent uses the interface to issue commands rather than just, like using normal bash commands. It's different kind of control sequences. And it also gets back the feedback in a language model friendly way. And for the next few slides, we'll look at some examples of interfaces that we tried. And it's one of the strengths of the SWEAgent paper that we have very detailed ablation studies, so that we really, dig into like what's really working, why is it working, and what doesn't work. To give an overview, the interface that we provide has basically 4 or 5 parts. There's a file viewer, so we have a notion of an open file, just like in, let's say, VS Code. You're usually looking at one file at a time. And then it stays open, and you can, scroll up, scroll down. That's also possible for the language model to do. And at any given point, you only see a certain window here. And you can go to lines, and you can search in the file and so on. But then in order to know what file to open, you also need to find files. So we have a find file command that's slightly easier than normal find. You can search to the directory, you can search a file, and so on. So for the file viewer, the most important thing is that it's a limited window size. And we also ran some studies of how many lines at a time are optimal, and came out with 100 lines. So you actually can see that, like going to 30 lines is really strongly degrades the performance, but also going to 400 lines is really not good. And obviously, sometimes if you cat the full file, and I don't know, if you're working on pandas data frame, I think the data frame.py is like 10,000 lines or so. It's just, like your language model should never just cat the whole file, and that would just flood the context window. And there's like small things here. So for example, repeating the name of the file that's open, stating the total number of lines, and also that we simply show that there's more lines above and more lines below. Because if you don't do that, sometimes the language model would just assume that the file, ends at this very last line that we show. Of course, the numbers here also provide then context for like go-to operations and similar things, and it can, remember where certain stuff was written if you want to go back there. Search, already talked a little bit about kind of the shell-only approach, where you just, like use whatever it's built in grep. We also compared that with what we call UI-inspired search, which is, if in most editors, if you search for a string, we jump to the first find, see the context there, and then we have to navigate to the next occasions where this word has been found. This also didn't work so well with the language model. Actually, it's like a 6% point performance degradation, so it's really bad. Probably because it just needs, a lot of jumps, and it leads to very long trajectories, for example. But also in general, it really seemed like the best thing to do here was to show all the results at once, but not with context. So you just really show where things are, and keep all the context to a minimum to avoid confusion. But even there, like if the search prompt is too general and you get too many results, then this would not be useful. So there we actually tell the agent to retry. So a lot of this is kind of this management of, you really try to limit the information that's displayed at a time to the minimum that's, or like to the optimal amount for the agent to make sense of. File editing. So this is actually the hardest thing of them all. A lot of optimization went into this. What we ended up with is basically a blockwise editing where the agent specifies a line window. So for example, here, edit 404 to 407. So it wants to edit those 3 or 4 lines, and then it gives us a replacement text that will be put instead of these lines. Now, I think meanwhile, so the SWEAgent paper is already a couple of months older. It seems like that's the most predominant editing action that's being in use by agent. It's actually more like a classical search and replace thing. Like you have like a search, like this would be like you would search for the original term and then replace it with that. But generally, editing is very error prone. So language models are not great at this, and this is something that needs really to be fine-tuned. Well, I should also mention that shell-only editing is basically not working at all, because if you don't have interactive programs, the only way to like do it with classical shell is like set expressions or other regular expression-based things. So that's not working at all. So the main two things, or the main thing that we introduced was a linting step after every edit. So for example, here, if you don't have linting, and it's going to edit it, and it's going to have 2 closing braces here, that's a syntax error. So we just block it from actually making those edits take effect. We tell it what the syntax error was, and we tell it to go again. So for Python, we just use SWEAgent with a very limited subset of error codes that we're looking for, because you don't want to be too strict and like go into I don't know, like code quality issues. You really want to block it from doing something that makes the code inexecutable. One thing, for example, that's hard for language models is to get the indentation right with those kind of editing commands. So I think that's maybe one of the most frequent cases where we really block, if it just gets the indentation wrong and then it tries again, and usually manages to fix that. And so linting alone made like a 3% point difference in the performance. Now going to the overall control flow. So we start SWEAgent with a system prompt. We describe the overall setting. We tell it that it's a software engineering agent. We provide some general instructions. We can look at them in a second. And we also show a very brief documentation for all of the different commands that we give it. Then comes the demonstration, which is basically a slightly compressed version of a full trajectory of a successful solution attempt to a problem. And then we have the issue statement. So this is kind of the initial prompting to the model. And then SWEAgent will suggest the first thought, what it wants to do, and an action that's being executed. and every action has then a response from the environment. It might be, like confirming that the file has actually been edited or something like that. Now, so you get all of these thoughts and responses, and that just keeps on going on. And at some point, your this whole history that you have to feed to the next step just gets larger and larger, which both makes it costly, but it also causes issues because models are just not great to deal with very long context at a time. So there's a couple of tricks here that we do to slightly compress the history. For example, whenever like an edit fails, so we have format errors, once it corrects them, they are removed from the history. We also collapse old observations, as in we just omit them, so there's only the thoughts and actions, and maybe a quick stop saying like that the response has been omitted. And so we generally only, at like the later steps, we only show the last 5 outputs, and the rest is kind of elided. But there's also, really small things that you have to pay attention to when developing agents. Just to give a quick example, a lot of commands, like for example, running a Python file that's supposed to reproduce the issue, but maybe if the issue has been reproduced, there's actually no line of output. And this can really confuse GPT-4. It just assumes that the command never ran because there's no output. So, like small things like making sure that we notify the model explicitly when there's no output produced helps, because sometimes you just get like stuck in very silly loops. So I think a lot of the agent development is about like looking at those things that go wrong, or where the language model really is confused about minor things. Right. So you actually see here on the left, that collapsing the history is like a 3% point improvement. Obviously, it can also be even more clever, but we found that this kind of simple thing of keeping the last 5 things works relatively well. Now you can analyze statistically the pattern that unfolds when you just let SWEAgent now run on SWE Bench issues, and it seems relatively reasonable. So this is a really it's a plot with a lot of information in it. So on the x-axis, we just have the turn. Like we start with kind of step 0, and then every time we prompt GPT-4, it's the next turn. And on the y-axis, we have the total frequency. So it's not normalized, which means also here you can see, like a lot of the later turns, they aren't used so often because, most models actually, on most instances, we submit before we get to, I don't know, turn 15. But if you look very closely, you can see that like it's a very frequent pattern that we first have a lot of kind of search operation in step 1, or even more frequently, create file, which is if the agent can directly create a reproduction script. Usually that's because in the issue, oftentimes people already have a small reproduction script. In that case, the agent will start with creating and then editing, which is why we have this very strong edit big thing here, and then we'll try to execute it. So that's why we have the sequence with create, edit, execute, and then we have most of the search operations. So overall, this seems to be very reasonable what's happening there. But like just looking at these statistical things is also interesting from a performance optimization perspective, because one thing that we find is that oftentimes, or at least SWEAgent succeeds very fast, but fails slowly. So meaning that here in the histogram, the light blue things are failed solution attempts, and the gray bars are successful attempts. And we see that kind of the peak of, like most, like if you look at the cumulative distribution, you'd see that most of the resolved issues definitely don't need more than 15 steps. But there's a lot of issues where if it doesn't solve them, it just keeps on trying until it gets like to step 35 or something, at which point we usually just cut it off because it's, it's expensive. So, you can optimize on that depending on kind of like the trade-off between cost and, you could rather just run it more often rather than like have it keep trying forever. So I think looking very closely at these resolution histograms can be very enlightening. So I think this is the last slide on the findings. So maybe that's like a good point to briefly stop for questions if there's any. I wanted to do that before, but then didn't remember. Do we have any questions that we can take at this time?
No, I'm checking like YouTube and Discord, and no, we don't have any questions.
Okay, great. Of course, people can also file in questions later, open them in our GitHub repository, which I think is the best way to get answers these days. And feel free to just always jump in if anything is unclear. All right, so now moving to the more exciting, at least for me, part, which is talking a little bit about how to run SWEAgent and then actually doing it. So currently we have 3 installation options. The easiest thing to try it out is all in browser with GitHub code spaces, which gives you basically a small kind of VS Code-like editor in the browser with capability to actually execute stuff. However, the default way to use it really is a local installation with pip. If you have issues with that, we do offer a fully containerized solution in a Docker container, but we don't really recommend it. I think the default should be to just locally install it, and it should be easy enough. So we have quite verbose documentation, and I'll just flash it every now and then. That covers all of the relevant steps here. There's also 2 interfaces. We have a command line interface, which has most of the features, and we have a web-based graphical user interface, which also works with GitHub code spaces. That's fun for demos and to get like a quick look at it. But again, like most of the features are in the command line interface. Now let me actually show you how you can start the GitHub code space. So for that, if you are at our repository, let me make that a bit larger. So we at princeton-nlp/SWE-agent. You'll see you have to be logged in to see that. You see this big green button code, which not only like by default it will show you the cloning options, but it also shows you this code space tab here. And what you can do here is just click the plus to create a code space. We also have a big button down here in the README. So both of these work, and it's usually going to take like a minute or 2, or maybe 3 to load. So I already did that before. Oh, but it stopped. Okay, so I'm going to click here, restart code space. This is probably what you would see in some form, except it might take a little bit longer on the first run. So I'm hoping that this will be a little bit faster. And a nice thing about this is not only can you just try out stuff here, but you can also directly edit the code and then observe the changes. And so the easiest thing that you can do here, it's already open, is to start the web interface. So you just copy the command that you have here, start web user interface. I think this is I already did it before, so I don't have to do it again. Let me actually see if this works. I might have shut down because the whole code space shut down before. But what you should see, and as a local run, is an interface that looks something like this. Yeah, we would have had to restart this. We have a tab for the problem source. You can either just write here, or give it the URL to a GitHub issue. We'll do this very issue from a command line in just a second. So we're not going to do the same thing 3 times over. you click run, and after a while, you'll see an output similar to this. So there's like a log file down here, which has like all of the detailed informations. You'll have the thoughts on the left side. So it, for example, starts here with, first, I'll list the files in the current directory to understand the structure of the repository. And here on the right, you see the output from the repository. And in this case, we actually just gave it an issue without any more information of how to set up the repository. So here, it's first going to realize that it has to install the package. So, it sees, oh, there's a setup.py file. It actually just, that might not have been necessary to open the file, but open it to see if like there's anything it needs to know or any dependencies. But then it just tries to run pip install -e, which usually installs everything. It succeeds, and then it jumps to creating the reproduce.py. That fills it in. So I hope this is kind of large enough for people to see. It executes reproduce.py, and it looks at those two outputs and compares them to the bug report, and it realizes that it has in fact reproduced the issue, and it just starts. Let me go up. Then it starts looking for relevant code. So I think here it kind of knows kind of from the issue already kind of which file to look at. But it still searches. It opens the file, and then it kind of looks for the right bit of it and starts editing and then rerunning the reproduction script and so on. Okay, so this is the web interface. I guess we can reload the space, but it will take a little bit of time because it died earlier. So instead, let me show you doing the same thing from the command line. So we saw the web user interface. And maybe before that, let's actually take a look at the issue that we're solving here. So this was this issue from Django. It's about serialization and deserialization of this extra tag field. And there's like I guess a corner case when it's an empty string. You see there's a little bit of description. And there's also the reproduction script given, which obviously helps the agent a lot. Now, to run this from a command line, you just, you clone and install our project, call run.py. You give it the model that you want to use. Obviously, you have to set up the keys at some point, either as environment variables, adding them to a file. We give it the path to the issue. Here, this is our own fork of Django, just so we have the repository at the correct commit, but the bug is not fixed yet. And here, just for demonstration purposes, I explicitly give it a small config file with the way to set up the environment. So if you run SWE Agent on the benchmark dataset, SWE Bench, this is all done for you. You don't have to care about the setup. If you run on your own repository, you can just have it try. If you have a simple Python repository, it's probably going to find out how to just install your stuff anyway. If it's slightly more complicated, like you can just write down, either with a shell script or something, how to install it. Okay, let's switch to the command line. I hope that is large enough. So here I just copied the very same thing, except that we're getting our GPT-4 from Azure. But let me just hit enter and hope this works. So it's first going to dump all of the config file here. So that's also part of the log. Now let's hope my Docker is working. Yes. So it just started a Docker container to use as a sandbox to execute all of the code in. It initialized that, so that took some 10 seconds already. And now it's cloning Django. The next step, which sometimes can take a while, is it sets up all the dependencies for Conda. For Django. So it creates a new Conda environment. Pip installs everything that there's to be pip installed or Conda installed. We might be looking at some 10 seconds here, depending on how much load this hotel Wi-Fi can take in addition to the live stream, because I guess it has to pull a lot of packages. Okay, so we got all of the dependencies. Now we run basically the last step, which is pip install -e. It's very important that we have this editable install, because we want to have any edits to the to Django to directly take effect, of course. So again, might take a couple of seconds.
While this is installing, I have a question. Can you like set up this and this as like a GitHub action, so it will pick up new issues on your repo and on the runner from the GitHub action?
So this totally works, and it's something we've been thinking about. I think the issue is, of course, who's going to pay for that? What happens if someone just creates 100? Like, what if someone just spams issues in your repository, and you just keep on paying for, like, for SWEAgent to fail on them because they might not be genuine? So I think it's more an issue of kind of logistics. There's nothing technical that stops you from just running that. So, I mean, it runs Docker, but you can run Docker in GitHub Actions. It's actually relatively simple. So I think, oh yeah, so basically, whenever like our continuous integration already makes use of that. I mean, it runs SWEAgent in a GitHub action runner, so it would be exactly the same thing as doing that. So perfectly possible. All right, so SWEAgent has finished. There's a little bit of an error here, which is totally unrelated to SWEAgent, unfortunately. So let me step back through this. So basically, the model went through, like found the right file. I don't know if I can see the edit bit. There's just a tiny edit to be done here, like lines 22 to 23. It replaced those. It added like an extra check that, this extra tags thing is not none. One of the things we do is whenever we have SWEAgent edit, we then show it the changed file, or at least like the context window, the appropriate window around the edit, so it can check again that it did what it wanted to do. And in this case, it confirms. We updated the code to check for this none thing. It again runs the reproduction script. This time the output changed to true false, which I guess is what we were looking for. Then it removes its reproduction script because it's no longer needed, and it calls submit. And here again, we see kind of the patch, which only changed one line. Now there's a little bit more output here. We save the trajectory. That's just like a big JSON file that contains all of the steps and all of the information to understand what's going on. We also solve this patch above, and there's also like a little bit of a blurb to show you where to find the patch and how to apply it to a local repository. There's also a switch to automatically apply to a local repository if you want that. It's just like here for the demonstration, I wanted to automatically open a pull request. And I think this all was fine, except that we reached some timeout when pushing things to GitHub. I think this is because network issues with the hotel, because I'm live streaming and then, like pulling a lot of stuff and interacting with GitHub. We might just run it again, but I can also show you what the result is. Actually, let me run it again in the background just so you'll see that I'm not making this up. I just have to add the, that it doesn't skip, usually it skips existing trajectories. So just to do this again, I'm going to add the no skip existing flag. Anyway, that's going to run in the background. But just for an interest of time, what the output of this would be is a pull request like this one. So this was also opened by SWEAgent, but the last time I gave a similar tutorial. So here, SWEAgent PR to fix, and then the commit message. It tells you that it's like this AI tool, and actually also gives you the whole thought process. So here we have another way to check kind of how it created a reproduction script, how how it put in the reproduction bit, then it executes that. Or it actually searches for the file that it suspects to be the source of the issue. Then it opens it here.
So Kilian, do you mind if I jump in with a question?
Yeah.
So regarding this thought process, like I had an early experience with SWEAgent that was kind of illuminating, where like I ran it and it like came out with this, like on a Hacker Cup problem, this like very well thought out process, and I'm like, like this agent really seems like it's onto something. But then like one of my colleagues called me out and told me like actually the model is doing worse than a coin flip. And I'm like, interesting. And so I'm curious, like as you're going through traces like this, how have you, like, I guess you yourself not fooled yourself? And then two, basically give the model feedback that, hey, like your thinking process is incorrect. Like basically, if you could sort of tell it, hey, like maybe annotate it and refeed it back, like kind of talk a bit more about that flow.
Right. Yeah. That's certainly an important part of the whole development process to kind of, refine the behavior of the agent. So I'm not sure what the coin flip, how you get to like the comparison to a coin flip. I guess that might be specific to.
Oh yeah, I
the challenge.
So basically the answers are either yes or no for like a few hundred test cases. So you basically flip a coin, yeah.
Okay, yeah, that's of course unfortunate. So sad to hear that I didn't solve that out of the box. So of course, how we verify for us is just unit test, like similar to how you do it. We'll talk about configuration options in a bit. Like one of the things you can do is amend the guidelines. You try to kind of tweak the behavior in a way that maybe it tries harder to verify. You can use different demonstrations that kind of really, like get it to use a certain approach on certain problems within context learning. You can see if, of course, like the thought process really comes from GPT-4. So that's, that's hard to, I think that's like the final bottleneck. It's just the capabilities of GPT-4, unless you want to like bring in a second agent and, like review the thought process and give feedback. In some ways we already give feedback, like like with editing, like whenever it tries to do something really stupid like mess up the indentation, that's just blocked and it tries again. But yeah, generally, SWE agents are a relatively linear thing, as in like it's a single agent and it really mimics a single human developer. And just like a human developer, you try to adjust the config, or well, okay, you can't do that with a human developer. You'd like give it better demonstrations or like more tips on how to proceed. Oh, okay. Great.
Yeah, I will read them out. Yeah, we have a couple of questions, and maybe I can pass them out. Yeah, people are asking like how many trials for success to count, and how many, like what's the average rounds that it needs to solve a problem.
Okay, I guess that depends kind of on the benchmark that you're trying to solve. So when we report numbers on SWE Bench on solving GitHub issues, I mean, it's a pass at one thing. So, like you run SWEAgent on all of the issues, you get like a solution attempt for every issue, and it either works or it doesn't. So unless the, like once the agent submits, it's submitted. You can, of course, build more complicated systems out of SWEAgent, where you have it run multiple times and, see if you can, without using truth information, determine if any of these, like to pick the best solution. But yeah, I guess that might be different with different kind of challenges if you can submit multiple solutions. Or was it more like about the development workflow? So for SWEAgent, actually, all of the studies that we showed, we optimized on a dev set and only then switched to the test set to not kind of have some fine tuning on the test set.
Okay, there's another question that it's more about. You have noticed trends on problems that SWE agents cannot solve. maybe you are gathering that, or maybe creating a data set of like, oh, these are all the hard problems that we are not currently capable of solving, or
all the submissions are to SWE Bench are public, so you can check exactly. I think so. John Carlos built this really nice thing on the SWE Bench website. See if it loads. Basically, there's on the website there's an interactive tool where you can explore which issues have been solved by which team. So not only by SWE Agent, but also by all of the other agent teams out there. I think you can even see, you might even be able to see trajectories directly from the web interface. But all of this is public. I'm not sure why this is not.
We'll check it out. That's really
loading.
Interesting. Like,
yeah, there's also this repository here, like SWE Bench experiments. Like this has all of the, whatever is listed on the leaderboard. Now we get the leaderboard. So this is the SWE Bench leaderboard. You see there's like a lot of submissions. There's 3 different subsets, unfortunately, of the SWE Bench dataset, Light being the most popular. And then SWE Bench Verified was only released a couple of days ago and only has issues that are human guaranteed to be actually solvable. A lot of these, like all of the top models, are closed source models. But I think, how do I do this? Maybe if you click on, here, like up here, there's an analysis tab. And I think here you can actually, you can select dataset and agent team. You get some metadata. It's gonna show you kind of aggregated by repository, which repositories are easy to solve and what percentage we get. Also by year to make sure that like there's no contamination going on. I don't know. I thought, there's like a button here with logs and stuff. I don't know. Like there's a lot going on here, so you can really dig into that and answer that question in high granularity by yourself.
Okay, we have other questions of like installing Docker and like setting up the environment. I think those can be, we can pass them later, or we can chat about that on the Discord. If you are on the Discord, we can actually help people debug and get started with this.
That sounds good.
No,
there's a whole, just because the Docker issues do come up, we have a whole section in our documentation just on making sure Docker works.
I have another like segue on the previous question. I was looking for if the model struggles when like fixing a small bug that requires like changing a couple of lines on a file, or like adding a feature. Like an issue could be support this new whatever paradigm, and that requires touching and like a deep knowledge of the code base, like a senior software engineer that knows like how do you like, what's your experience with SWE and SWE Agent and those type of feature related issues?
I mean, it's obviously much harder, but the other thing I think that's gonna be an issue here is just from the way that SWE Bench evaluates things. So I already briefly mentioned, so basically I think it's not completely trivial to quantify that, because if you have a whole new feature and like a larger block of code and related unit tests, oftentimes those unit tests might be to some extent implementation specific, right? Because unlike a bug fix, you already have the interface and everything kind of set in stone. So you kind of know exactly what you're testing, and like the reproduction script will already do that. But with a new feature, that's not so trivial. So I think there might also not be that many good pairs of issues and pull requests in SWE Bench that are really suitable for this. So I'm not 100% sure if you have good data on that to answer that really empirically. Obviously much harder for just the reasons that you mentioned.
Cool, thanks.
Okay, just to flash okay, we're still not. Okay, just to flash the documentation because that already came up. We have a whole installation section here. You can select how you want to install. I'd recommend to install from source. There's also an installation tips section that probably should really be named Docker issues, because it's about making sure Docker runs. This is not SWE Agent specific. I think this is really installing Docker. I think most of this is also taken from the Docker documentations.
When you need NVIDIA Docker is even harder. Now let's continue and be keepers of time here.
Okay. So I see this actually. Did we start at? Is it already 55 minutes in?
Yep.
Wow. Okay.
It's
so I'm not
fine.
sure.
Go
You'll
ahead.
have to.
I'm not. We can stay 10 minutes longer. I don't mind.
Okay. So it might
I'm
run
here.
10 minutes over time.
We're okay. Like
I'm sorry about that. All right. So let me be quick about a few boring things. Just for ergonomics, you're gonna start looking at a lot of trajectories. We have a little bit of an inspector in the repository to make looking at these easier. Look something like this. You select a trajectory. It's just kind of like a nice conversational way to present what's going on, kind of what were the messages, or what were the commands that were being issued, what were the thoughts, what were the environment replies. Not too exciting. Another thing is, like all of our outputs in JSON, having a good JSON viewer, like this online editor that actually shows you line breaks, is a real lifesaver when working with this. Now let's quickly talk about the implementation. So that's going to be relevant if you actually want to modify it, but I think it also informs you a little bit of, how the configuration files come into play. So the central entry point here is this run.py, which has a ton of options. Just run it with --help to see all of them. But when you run it, the first thing that's going to happen is it's going to set up the environment. This was the step which took like 10 to 20 seconds at the beginning. So that means it's going to start a Docker container. It's going to install the repository, and it's going to execute a lot of the installation commands to set up the repository. So here's our Docker container now. And the important thing here is that there's basically one shell session in the container that we keep alive during the whole process of solving this issue. So, every time we execute a command, it means we basically more or less copy paste this command into this existing shell session. And we use it to first set up conda and then install everything. Now, the second big class, so SWEAgent is the Python class. The second important class is the agent class. And this is configured by this config.yaml file that we'll see in a second. But there's basically only one important method here called forward, which takes all the history that we had, gives it to GPT-4 or your language model of choice, and prompts it for the next step. So to do that, we take all of the history, all the steps that have happened, and like the initial prompts, we put it through this thing called history processor, which by default kind of is pretty trivial. All it does is it kind of omits all the old outputs, only keeps the last 5 outputs. There's a little bit of cleanup, removes like kind of all the failed edits. But like tweaking this can also be a powerful tool. Now we're at the language model, and it's going to give a reply. So it's going to give its thought and its actions, hands it back to the environment where we execute the command, which again means more or less that we paste it into the shell session and execute it there. And it's also in this Docker container that a lot of our custom commands, like all the custom find and edit and so on commands, they all live here in this Docker container. They're not part of the kind of the big Python part here. So keeping this a little bit in mind that like we have those 2 classes and also the history processor. But then the tools live in the Docker container. I think that helps you get started. Okay, so let's jump into, I think, one larger example of how to modify the agent, which I think will tie all of this nicely together. There's 3 important configuration bits. There's this config.yaml. It contains all the prompt templates. I think that's going to be the number 1 thing that you're want to change. And also has the link to the demonstrations that are being used. The demonstrations have its own JSON data file. And the third thing is modifying the commands or the behavior of the commands. So all of the commands are in this config /commands folder. So what we're going to do as an example that touches all three, so you're going to add a new command, print cat, and all it's going to do is print that little ASCII art of a cat for morale boost. So this is the kind of hands-on bit. So let me make this larger. So here you see the defaulted YAML config bit. You see our system template here. You see a couple of things that you kind of fill in, mostly like the command docs here. So that's kind of the documentation of using the custom commands. Now to follow up with our task and create a new command, we look at the config directory. There's like this command subfolder here. For example, you already see like this edit function here. And we'll just create a new file, printcat.sh. I'm a little bit lazy. I'll just copy that in. So here, you see that the printcat function is super basic. It's just an echo statement. And you see a little bit of boilerplate here. We give it the signature of how to use this and also a doc string. And it's this doc string that will be included here in the command docs. Now, we also need to make sure that the agent knows of this command, or we need to explicitly tell it that this is like the printcat file is part of the commands. So there's a list down here, command files. I'll just add printcat.sh here. And now the last thing, so now the agent will know of the existence of this command, but it doesn't mean that it's going to use it, because honestly, it's kind of useless. So what we're going to do is you're going to modify the instance template. So this is the bit that has the issue, and then like the initial instructions and important tips. And we'll just add a 0.7, like very important before starting to solve an issue, always run the printcat command for morale boost. Okay, so hopefully that will be all that we need. So we added a new command file, make sure we added it to the config. We also put it in the instructions. So now let's just run over the same thing as before, and let's just see if it's going to print the cat at the beginning. So, should have probably picked like a simpler thing where you don't have to wait for 20 seconds to set up the environment. Actually, so if this is an issue, if you're working on a project that has like a long setup step, ooh, that didn't seem to. Okay, that seems again to be a GitHub issue. Could not resolve host github.com. I don't know. There seems to be like some issues with reaching the GitHub domain from this laptop, from this hotel network. Let's just try again, because this worked previously. So
I think that GitHub was down some part of the day early this morning.
Oh, okay. Now it.
Maybe it's that. I don't know.
Okay, now we're one step further. Except that probably during the installation step, it might clone a bunch of more things. But basically, what I wanted to say is, if like those long setup times are a problem, and maybe you always run SWEAgent on the same project, what you can do is just create a custom Docker image that has all of this pre-installed, and then basically it's gonna immediately start working on that, and you'll solve those 20 seconds.
The image gets cached anyway, like even if you rebuild and you have no changes, like the last command is probably copying your Python files in there. So
in our case, we have a couple of more command line options where you can enable caching either by task or to speed it up. I don't think it happens by default, which is why we're sitting again at like 20-second wait time, I guess. Of course, like the Docker images building. Oh, okay. Here you see. To start solving the issue, let's first boost our morale by using the print cat command. Okay, beautiful. So I think, let me quickly switch back to the slides. This should be almost our last thing, I think, in the interest of time. So of course, this is going to be about coding problems, where SWEAgent is going to be used in the hacker challenge. So we prepared a little bit of documentation of how to repurpose it for that. Right now, if you want to solve any kind of, like, let's say, code competition things, you start with creating an empty repository and put your problem stub in there, like, for example, like this class solution and just the signature, and put your problem statement there. And then you run SWEAgent like normal and just give it the path to the problem statement as a markdown file and the path to the repository. And we also have a separate configuration file that's slightly more tuned to coding challenges. You should also probably specify this apply patch locally thing, which means that rather than just producing a patch, it's already going to apply the patch to this little test repository here. So I think ergonomic-wise, this is not perfect because you have to create this repository. I'm hoping to add like a kind of simple batch interface for coding challenges soon, so that, I don't know, if you run over 1,000 lead code challenges, you can just do that. It's also in the documentation. So I'm not sure if how the slides will become available, but we have in the usage section, we have solving coding challenges here, which contains the exact same information and some more tips, and you see some example output here. All right, and that brings me to my summary. Again, sorry for running a little bit late. So I think what makes SWEAgent interesting, and even though now there's a lot of different agents, I think it's still of relevance because it kind of has this kind of very free-flowing execution. There's no hard-coded pipeline in there, but it really behaves kind of like a human developer that is guided by some tips and demonstrations. And it also makes it really easy to modify it to do tasks that it was not necessarily meant to be, especially because you can also add more tools for other things. Hopefully easy to install. If not, let me know. I've been working a lot on the documentation, so I think we cover most things there now. And we talked a little bit about the configuration options. There's a lot you can do there. But then also, I think the implementation is pretty easy to hack. I think the agent class is like 1,000 lines or so, and that's probably what you'd start by modifying. So thank you for your attention. If there's any more questions, very happy to take them here, or I heard someone mention a Discord. If you post later on Discord, I might answer them tomorrow because it's 11 p.m. here in Bangkok. And then there's always the GitHub issues. I think those have the highest chance of being seen by me.
Thank you very much. I think it was really interesting, and yeah, we'll definitely give it a try. I think as large language models will get better over time, this will be more and more capable. And I had a final question that maybe Mark